In today's video, we're going to take a look at moments, which can explain things like why a longer spanner is easier to use than a short spanner, and how two people with different weights can balance on a seesaw. First though, we need to look at what exactly a moment is. We can describe a moment as the rotational or turning effect of a force. For example, if we had a spanner that we were using to tighten a nut, and we applied a force downwards at the end of the spanner, then instead of the whole spanner moving downwards, it would just turn around this central point, which we call the pivot. And it's this turning effect that we refer to as the moment. In order to work out the size of a moment, we need to use this equation here, which says that the moment is equal to the force that's applied times distance. And importantly, this is the perpendicular distance between the pivot and the place where the force is being applied. So to get the biggest moment possible, you should apply a big force far away from the pivot. Now, the fact that we use perpendicular distance is actually really important. Perpendicular means at right angles. So you have to measure the distance at a right angle to the direction of the force, which in our example here is basically the whole length of the spanner. However, if we applied the force at a weird angle, like this instead, then our perpendicular distance would be much smaller, which means that the moment this creates would also be much smaller. Let's try to calculate our own moment. Imagine that you apply an 80 Newton perpendicular force to a spanner 20 centimeters from the pivot. What moment do you generate? First, we need to check our units and change the 20 centimeters into meters, giving us 0.2 meters. Then we can just multiply this 0.2 meters by 80 newtons to get our answer of 16 Newton meters. Now, what if you wanted to generate that same moment of 16 Newton meters, but by applying a force 0.1 meters from the pivot instead? To calculate the force required, we'd have to rearrange our equation to get moment over distance equals force. Then we just plug in our moment of 16 Newton meters and our distance of 0.1 meters, and would find that the required force is 160 newtons. So we had to apply a bigger force to get the same turning effect, because we were applying it closer to the pivot. The last concept we need to look at is that you can sometimes have more than one moment acting on the same object at once, like in the case of a seesaw. Here, the pivot is the middle, and so if we apply a force over here on the right side of the pivot, the perpendicular distance will be this distance here, between the pivot and the force. So if this was 2 meters, we would have a moment of 2 times 600, so 1200 Newton meters. Because moments are turning effects, we talk about them in terms of clockwise or anticlockwise, rather than up or down. So comparing it to our pivot, we can see that this one would be a clockwise moment. Whereas if we applied a downwards force to the other side, this would create an anticlockwise moment. In order to work out the overall movement of the seesaw, we're going to have to take into account both of these moments and see which of the two is bigger. If the two moments are both the same size though, so the total anticlockwise moment is equal to the total clockwise moment, then the seesaw won't move at all, as they'll perfectly balance each other out. For example, in this case that we've drawn here, how far from the pivot would the 800 Newton force have to be in order to balance the seesaw? We know that the total clockwise moment is 1200 Newton meters. So to make it balance, the anti-clockwise moment is also going to have to be 1200 Newton meters. To find the distance needed for this, we're going to have to rearrange our equation to get moment divided by force equals distance, which will be 1200 divided by 800, so 1.5 meters, which means that we'd have to apply the force 1.5 meters from the pivot if we wanted the seesaw to balance.